Good afternoon, everybody. Now then, I'm going to talk to you about mobile network, which might seem a curious thing to talk about in an Institute of Navigation course. Accountex is a timing test and measurement company, and we cover the T of the PNT triad. So I'm going to tell you, primarily, we deal with testing of mobile networks and timing in mobile networks. So I'm going to tell you a little bit about why we need to do that. So my agenda will cover synchronization in mobile networks, both frequency and time synchronization. We'll have a look at 5G networks, and then what's this got to do with GNSS systems? So synchronization in mobile systems. But initially, when mobile systems first came out, it was frequency synchronization that was most important. The principal requirement for mobile systems frequency synchronization was that the RF carrier frequency, the transmission frequency, must be within 50 parts per billion of the nominal value. So that means if you're transmitting on 1 gigahertz, you've got to be within 50 hertz of that carrier frequency. And there are various reasons for it. One is simply regulation. You know, spectrum is a very valuable commodity, and mobile operators paid a lot of money for spectrum, so they expect that they get exclusive access to that spectrum and that other operators are not off frequency and therefore stamping all over their own spectrum. Because if they do that, that causes interference. So interference with other base stations or other operators. It also enables handoff for mobiles moving between cells. If one cell is off frequency, the mobile might not be able to connect to the next cell as it moves from one to the other. So in that sense, it's a quality of service issue. And the final reason is the Doppler effect. Mobiles are mobile, they move. And so they experience Doppler effect just like ambulance sirens that go up and down in pitch as they go past you. So a base station carrier frequency accuracy is about 50 parts per billion, and the handset frequency acceptance is about 250 parts per billion. That means that there can be a Doppler shift of up to 200 parts per billion between the two, and it should still work. So for those of you who remember high school physics, that's the equation for Doppler shift. For change in frequency is equal to the carrier frequency times a change in velocity over the speed of light. So at 320 kilometers per hour, which is roughly the speed of the TGV in France, that's about 200 miles per hour, then you might well get a change in frequency of about 300 parts per billion. So that really takes it outside the range that a handset can actually accept. Of course, geometry plays a role here. If you're heading straight towards the transmitter, then you'll see the maximum Doppler shift. If the transmitter's off to one side by some distance, then the speed that you're moving towards the transmitter is less. So Doppler shift would also be less. If you're on the motorway, if you're driving at 100 miles per hour and you're speaking on your phone, then firstly you should be arrested, but your mobile will probably work because that would introduce a change in frequency of about 150 parts per billion, which is within the allowance. Time synchronization then. So for the GSM and UMTS systems, that's the second generation and third generation mobile standards in Europe, there was no requirement for time synchronization. It was only frequency synchronization. In North America, though, they had a different system. They had the CDMA-1 and CDMA-2000 systems. And their base stations had to be within 3 microseconds of system time, or they were allowed up to 10 microseconds if they went into holdover. And being an American system, they used GPS systems at every base station to provide the system time reference. So effectively, the system time for CDMA-1 and CDMA-2000 was GPS time. And there they required it for what was called soft handoff. So the way that they would decide which mobile base station to talk to was that each base station would transmit a pilot signal, and that pilot signal would be synchronized, and it would arrive at the mobile. So you can see a picture there of a mobile between two base stations, and the blue one on the left is slightly closer, so you would expect the pilot signal from that base station to arrive before the one from the green one on the right. Now 3 microseconds, which is the time accuracy that's required, roughly translates to about 1 kilometer of distance. So if you're any more than that, it will look like you're either 1 kilometer closer or 1 kilometer further away than you actually really are. So you'd start talking to the wrong base station. So that's the principal reason why they needed time synchronization. When we came to the 4th generation of mobile systems, the LTE, there were 2 variants of that. There was FDD, frequency division duplexing. So that was where you transmitted upstream and downstream transmissions on different frequencies. And that had the same 50 parts per billion requirement for frequency synchronization. But it didn't have any requirement for time synchronization. Some operators, principally in China, used TDD, time division duplexing, where they did upstream and downstream transmission in different time slots. And they required 50 parts per billion as before for frequency, but they also required phase alignment between the neighboring base stations. But as I said, there wasn't much deployment of LTE TDD in, certainly not in North America or Europe. It was mainly deployed in China. So the reason why it needed synchronization was, as I said, for TDD networks alternate between upstream and downstream transmissions. So you can see in the top diagram, got the base station transmitting in the dark blue, and then the user equipment or the mobile handset in light blue, and there's a guard period in between the 2 transmissions. If there's a nearby base station that has a synchronization error, you can see the effect in the second diagram. So there's a blue base station and the green one. And if the synchronization error is too big, then the green base station will start talking over the top of the handsets. Now that's a problem because the handsets generally have a much lower power signal, and therefore you'll start to see interference. So the time synchronization must be better than the smaller than the guard period. So the synchronization requirement for LTE TDD is expressed in terms of what's called cell phase synchronization accuracy. And it says the maximum absolute deviation in frame start timing between any pair of cells on the same frequency that have overlapping coverage should be less than 3 microseconds. And it's a bit of a mouthful, but basically it says each base station should align its transmissions to within 3 microseconds of any other base station. So it's a phase requirement. It's relative to the other cell. It's not a time requirement, but it's normally implemented as a time requirement. The best way to implement it is to have a central clock, and that central clock transmits a time signal to each of the base stations in the network. And provided every base station is aligned to within 1.5 microseconds of that central clock, then they should be aligned to within 3 microseconds of each other. So that's the 1.5 microseconds is a time accuracy, but that's as a convenience in order to be able to get the phase alignment. So what about 5G then? We're hearing a lot about that recently, and it's starting to be deployed in most countries now. Well, 5G, as I said, in most previous mobile generations, most operators deployed FDD, and there were no time synchronization requirements, only limited TDD deployments. That's changing with 5G. For 5G, and we call it NR, new radio. Now 5G new radio, most deployments will be TDD. The cell phase synchronization accuracy is still 3 microseconds, so it's the same requirement. The The difference is this will start to become an interoperator and hence a regulatory requirement as well. And I'm going to explain that better on the next slide. However, there are also some advanced techniques such as carrier aggregation, which is bonding two carriers together to make a big channel, and positioning requirements as well, that require even tighter accuracy, potentially as low as 100 nanoseconds. So you can see that it's a lot harder to meet 100 nanoseconds using a centrally located common reference clock, as was normally done with LTE TDD. So this point about interoperator synchronization that I mentioned, one other thing about 5G is that operators want to remove frequency guard bands. So you can see a diagram there, and you can see 3 operators all allocated 100 megahertz of spectrum, but they're only able to use 80 megahertz because they have to have a guard frequency band between one operator and the next. So they're losing 20 megahertz of spectrum. And they had to do that when you are operating FDD systems, because obviously there would be interference there. With TDD, they can actually operate without frequency guard bands. So they gain an extra 20 megahertz of spectrum. But they can only do that provided all operators agree to synchronize to the same time reference, for example, UTC. Now, currently in Japan, there's a kind of gentleman's agreement between all the operators to all synchronize to within 1.5 microseconds of UTC. European operators are also raising the topic as well, and it's thought that this will eventually become a regulatory requirement for 5G TDD operators. So it's going to become something that's going to need much more sort of testing and measurement, and to ensure that all the operators comply with that agreement. I also mentioned carrier aggregation. So carrier aggregation bonds two small carriers together to make one big carrier. But the radio frames on each carrier must be aligned to within 260 nanoseconds, and that's called the time alignment error. Now, normally they're transmitted from the same antenna, so it's not a network synchronization problem. So you can see here, there's a transmitter, it's transmitting two 10 megahertz carriers to make a 20 megahertz pipe. So you get double the bandwidth down to the user equipment or handset. We can now move that one of those 10 megahertz carriers to an alternative base station. So now you've still got two 10 megahertz carriers, we've still got a 20 megahertz aggregated pipe, but the second carrier is transmitted from a different base station. So that means now there's a network synchronization requirement between the two base stations. That means to allow them to align their radio frame starts to within 260 nanoseconds. So that will make a big difference to the time accuracy that's required within the mobile network. And there's yet another requirement that's going to drive down the time accuracy requirements even lower than that, and that's positioning. So currently there's emergency legislation that says emergency calls require the operator to determine the position of the caller to within 50 meters. Now normally that uses the GNSS receiver in your phone to determine the position. That's the reason why we had GNSS receivers in phones originally. It was to meet the emergency requirements of the E911 legislation in the United States and similar legislation in Europe and other countries. But there's a problem because the GNSS receiver in your phone doesn't always work, particularly not when you're indoors. It might not be able to see satellites. So another method that operators can use is what's called observed time difference of arrival. So that calculates the position based on the time of arrival of signals from 3 different base stations. So you can see here I've got a black one, a blue one, and a red one, and the signal from each of those base stations will arrive at your phone, and based on the relative time of arrival of those signals, you can calculate your position. But in order to determine your position to within 50 meters, it requires the base stations to be accurately synchronized in time to within approximately 100 nanoseconds. So that's an even tighter synchronization requirement that's coming for in order to meet this type of emergency requirement. Of course, it's not just emergency requirements, particularly in 5G. There's the intention and the hope that we'll be able to use positioning for lots of other services as well. It's not just Google Maps or things like that, but it's much tighter positioning requirements. So things like stock monitoring. Boxes or pieces of equipment may have tags on them that communicate over the 5G network, and they want to know where everything is. It might be autonomous vehicles, for example, maybe in an underground car park. Well, they certainly need to know their position to much better than 50 meters. But there'll be other techniques as well as OTDOA that are used to determine position with 5G. So what's this got to do with GNSS? Well, time is relative. There's no such thing as absolute time. All we can do is to count regular events. So like astronomical events, like days, months, and years, or physical events such as pendulum swings, quartz vibrations, or cesium atom resonances in the ultimate case at the moment. So common time requires everyone to start counting at the same point or epoch and count at the same rate. So for example, a calendar counts days, months, and years from a known starting point. Different calendars have different epochs. So the Gregorian calendar that we use for most things in this country is dated from the birth of Christ. The Islamic calendar just has a different starting point or epoch. It uses the date of the Hijrah. Provided you know what the chosen epoch is and what the counting rate is, then you can synchronize your time together. But you need a common reference in order to be able to do that. And the principal reference of source of time into the telecoms network is usually GNSS, because it's a convenient means of distributing a common time and reference over the wide area. It might then be distributed using a protocol through the network. And the one that we use mostly in the telecoms industry is PTP, Precision Time Protocol, which is documented in IEEE 1588. So you can see there the diagram. There's GNSS on the left, PRTC, which is effectively a GNSS receiver. We call it a primary reference timing clock in the telecoms world. And then we use PTP. PTP Grandmaster clock just converts that time into a series of packets that are sent over the network to the slave clock, and then to the consumer of time, the end clock, such as the base station. So all the GNSS vulnerabilities that you've been hearing about today, and probably also have heard about in other media, all those GNSS vulnerabilities applicable to navigation systems, they also apply to timing. There are a number of industry threats and vulnerabilities that are dependent on GNSS timing. Telecoms is just one of them. The power industry is also using GNSS timing. Financial industry uses it to time stock trades, for example. Transport industry is going to be using it. So there's certainly a lot of activity going into looking at vulnerabilities of timing systems that are based on GNSS. So for example, in the US, the Department of Homeland Security have a project going that's looking at the vulnerability of critical industry to GNSS failures. And that involves representatives from telecoms operators and vendors and the test and measurement community. In Europe, the GSA have initiated several projects looking at resilient GNSS timing receivers that might cross over into the telecom space as well. So to conclude then, accurate time is fundamental to the coming 5G mobile network. And if mobile networks seem like essential services now, 5G has ambitions to be even more critical to our modern life. And it's not just mobile networks, as we said, it's power generation, financial, automotive networks, manufacturing. They're all going to be dependent on GNSS for time distribution and subject to similar vulnerabilities as with any other GNSS-based system.